Hey there, and welcome to today's Explainer. We are tackling an absolutely massive subject today, and we're doing it by breaking it right down to the fundamental studs. We're going to dive into a full overview of Architecting Intelligence, a complete artificial intelligence compendium. Now, if you follow the tech space at all, you know the conversations around this are literally endless. But what this compendium offers is a radically new architectural blueprint for how we actually understand these models. We're not just skimming the surface here. We're looking at the foundational engineering of deep learning architectures, building a crystal-clear mental model of how artificial intelligence is constructed, parameter by parameter.
So, what actually is AI? To really grasp the current landscape, we have to just cut right through all those relentless corporate buzzwords and marketing speak. We need to look at what this technology fundamentally is when you strip it down to its core architecture. So we're moving way past the theoretical today and examining the literal engineering, how do billions of parameters interact to form probabilistic outputs. Ultimately, this is all about understanding the actual structural engineering of machine intelligence.
Here's the blueprint for how we're going to break this down. First, defining artificial intelligence. Second, the foundation, which is raw data. Third, the framework, or algorithms. Fourth, real-world AI applications. And finally, architecting the future.
Let's jump right into part 1, defining artificial intelligence.
A really great way to define artificial intelligence is as a constructed system designed to replicate learning and processing capabilities. You know, it's so easy to think of AI as this mysterious black box, right? But it's not. It's a highly engineered tool. The compendium frames this perfectly as a shift from deterministic programming over to probabilistic output generation. So we aren't building systems that know things the way you or I do. Instead, we're architecting systems that calculate the statistical likelihood of a correct output. And they do that based on just immense computational weight. It's basically mimicking cognitive functions through a highly structured, multi-layered design.
And this really highlights the contrast. Standard computing, which is rules-based, versus artificial intelligence, which is learning-based. This is a total paradigm shift in how we build systems. I mean, for decades, standard computing relied on hard-coded heuristics. A human programmer explicitly defined every single logical pathway. But a learning-based architecture? That changes the blueprint entirely. Instead of hard-coding the logic, engineers build deep neural networks. They define the architecture of the nodes and layers, sure, but the system itself actually determines the parameter weights during the training phase. So by adjusting billions, and honestly now trillions, of these internal weights, the system essentially writes its own probabilistic rule set to navigate incredibly complex problems that traditional heuristics could literally never solve.
Moving on to part 2, the foundation, which is raw data.
The number one, absolutely most vital building block for architecting modern intelligence isn't actually the code itself, it's the data. Without a colossal foundation of raw data, a deep learning architecture is basically just an empty skyscraper frame. And look, we're no longer talking about simple databases here. The compendium points out how modern foundational models require scraping essentially the entire digitized human footprint. We are talking petabytes of text, images, and sensor data. To put that scale into perspective, these datasets contain hundreds of billions of tokens. That represents everything from massive academic archives down to the entirety of public internet forms. This raw data acts as the concrete and steel of the operation. The system processes this immense volume to learn semantic relationships, syntactical structures, and complex visual patterns. Simply put, the scale of this data foundation directly dictates the structural integrity and the capability of the final model.
Okay, part 3, the framework, algorithms. This 3-step process really demystifies the back-end mechanics. Step 1, ingest raw data. Step 2, apply algorithmic framework. And step 3, output structured intelligence. So step 1 ingests that massive petabyte-scale foundation of raw data we just talked about. But step 2 is where the actual construction happens. This is applying the algorithmic framework. The compendium really highlights the massive leap forward brought by transformer architectures. Instead of processing data sequentially, one bit at a time, transformers use self-attention mechanisms. This means they weigh the relevance of every single piece of data against every other piece simultaneously. It's applying incredibly complex mathematical structures, utilizing techniques like backpropagation to continuously adjust those billions of parameter weights, refining the model's accuracy over thousands of computational iterations. And then finally, step 3, outputs structured intelligence. It takes all that chaos of raw, unstructured human knowledge and mathematically aligns it into a coherent, highly capable, probabilistic engine that is ready for deployment.
Which brings us to Part 4, Real-World AI Applications. The finished structure, applications impacting daily life. And let's be clear, these finished structures aren't just parlor tricks or your basic social media recommendation algorithms. The compendium details how this architecture is driving some profound paradigm shifts in really high-stakes fields. For instance, we're seeing these models applied to computational biology, successfully predicting protein folding structures in a matter of weeks rather than decades. That is a breakthrough that is fundamentally altering drug discovery as we know it. We're also seeing edge computing AI deployed in autonomous logistics networks, calculating millions of variables in real time to optimize global supply chains. These applications are outputting highly structured intelligence that seamlessly integrates into enterprise-level architectures, and they're shaping incredibly complex industrial and scientific realities every single day.
And finally, Part 5, Architecting the Future. So, what is our role in the future architecture of intelligence? We've explored the structural engineering of these systems, the sheer petabyte scale of their foundational data, and those intricate self-attention mechanisms of their algorithmic frameworks. But according to the compendium, the timeline for this whole construction project is accelerating exponentially. The parameter counts of these models are scaling up by orders of magnitude year over year. We are rapidly moving from specialized tools toward generalized cognitive architectures. So as these deeply integrated, multimodal systems become the foundational infrastructure of our global economy and scientific research, what exactly is our role? Are we just going to be the passive generators of the raw data, or are we actively defining the parameters of this new reality? How will you choose to inhabit this newly architected future? Thanks so much for joining me on this explainer today, and I'll leave you to think on that.